today's talk is going to be on plasmonic catalysis using hot electrons to drive chemical reactions. So first I start with a brief introduction to plasmonics. So what are surface plasmons and why do we care about them in various applications? Well, surface plasmons are the collective and coherent oscillations of conduction band electrons. Now you can have surface plasmon polaritons like here, where the plasmons propagate over distances of a few micrometers, and this is of particular interest for information transmission on a chip, for instance, provided a way could be found to compensate for the huge losses that plasmons suffer. And then you have the localized surface plasmon resonances in noble metal nanoparticles, where, as the name suggests, the collective oscillations are localized. And really it is more the LSPR, the localized surface plasmon resonances, that have been studied in catalysis and photocatalysis, although there have recently been some efforts to look at SPPs, the surface plasmon polaritons, also for catalysis. Now plasmonics is the quintessential nanoscale phenomenon. The surface plasmons are generated by nanostructuring metals. So so either you have thin films or gratings for SPPs, or noble metal nanoparticles for LSPR, and it's gold and silver that have surface plasmon resonances at visible wavelengths. And there's a few other materials which I point out here. You have the transition metal nitrides, titanium nitride, hafnium nitride, zirconium nitride, which are very interesting because they're ceramics and are a lot less expensive compared to noble metals. Also copper and aluminum, which are base metals, they do have plasmon resonances in the visible and the near infrared regime, provided they have very specific shapes and dielectric environment. So that kind of brings us to one more interesting aspect of plasmonics, which is its exquisite sensitivity of the plasmon resonance to the size, the shape, and the surrounding dielectric environment. So here you see the plasmon resonance of nanorods of, I believe these are gold nanorods, being tuned over a very wide range from green, from about 500 nanometers all the way to the near infrared. Okay. Now plasmons decay within femtoseconds, and there can be radiative damping, where the plasmon is just the light photon that stimulates the production of the plasmon is scattered, so the plasmon is re-radiated. But there are other mechanisms that are more interesting. So where the plasmon decays to form hot carrier pairs. So these are pairs of hot electrons and holes. And two important mechanisms here are Landau damping. So Landau damping, which is shown here, is essentially the intraband excitation of electron hole pairs as a consequence of plasmon decay. Another important mechanism is chemical interface damping, or CID, which occurs at an interface. So now chemical interface damping is very sensitive to the interface and hybridization of the orbitals and wave functions of the metal with those of the material it's in contact with, which is usually either an organic molecule or an inorganic semiconductor. And this is why DFT, or density functional theory, quantum chemical modeling, is an essential tool in the overall field of plasmonic catalysis. Okay, so now it's actually very difficult to harvest hot electrons, and the previous speaker, Professor Art Nozick, also mentioned about using hot carriers, but he was talking about semiconductor quantum dots and quantum wells to improve the efficiency of solar cells. Here, the goal is primarily to use the hot carriers generated in metallic or metal-like nanoparticles to be used either for electricity generation or for catalysis. Now, to appreciate how difficult it is to actually harvest hot electrons, consider the time scales of the processes involved. So, as I mentioned, if you're talking about the sequential mechanism, which is what occurs when Landau damping is the predominant decay mechanism, or the hot electron hole pair production mechanism, you have the excitation of hot carrier pairs occurring in a few femtoseconds, and then you have electron-electron scattering processes uh, which take place in about 100 femtosecond, which cool these electrons, and further cooling takes place through electron phonon collisions in about a picosecond. So the reason, remember, that the hot carriers are called hot is because they do not, the distribution of energies yeah, from in the hot carriers produced by plasmon decay does not correspond to a Boltzmann distribution at room temperature. Instead, it actually corresponds to a much higher effective temperature, and hence they are called hot carriers. However, what I'm showing you here in this slide is that within about a picosecond, which is 1/trillionth of a second, um, almost all the hot carriers have relaxed back to thermal equilibrium, and so that excess energy is lost. So it's back to a purely thermal distribution in a trillionth of a second. Now, it's incredibly hard to extract useful work from these hot carriers in 1/trillionth of a second. And so this is why it's very hard to harvest hot carriers. And so considering the difficulty that I just pointed out in harvesting hot carriers, when theorists performed calculations, they found out that even with when they looked at all the processes in the sequential mechanism being optimal, they found that it was very hard to exceed an efficiency of 77%. So 7%, which is a very low efficiency, because as Professor Nozick mentioned, photovoltaics, commercial photovoltaic devices already have a much higher efficiency. So 7% is really not something to be excited about. And that is what it seemed would be the maximum efficiency of hot carrier based photovoltaics or hot carrier based photocatalysis. But that changed. And so this changed a while back. So using femtosecond transient absorption spectroscopy, there were a number of groups that found that, especially in junctions of titanium dioxide with gold nanoparticles, um, the hot carrier injection yield, that is the number of hot carriers that could be harvested that could be separated and transferred to TiO2 before they relaxed back to room temperature, could be as high as 45%. So you show one paper which claimed a yield of 40% and another paper that um, showed electron injection efficiencies of 25 to 45%. So what's the reason for this? I mean, I just on the previous slide, theory suggested that 7% would be an upper limit, and here there are experimental studies that are showing a much higher hot electron injection yields, and the reason has to do with the mechanism. If it's not Landau damping but chemical interface damping, then it turns out that you can sidestep a lot of these relaxation processes and get much higher hot electron harvesting yields. And so in titanium dioxide, within about a few hundred femtoseconds, uh, the hot electrons in gold nanoparticles were injected into titanium dioxide in a few hundred. And so this is before picoseconds. This is well before cooling due to phonon collision. So coming back to the slide, this shows why the mechanism is important. So if you have a direct charge transfer mechanism such as chemical interface damping, there's a possibility to realize much higher quantum efficiencies and overall efficiencies for hot carrier harvesting. And the same thing can also be done in a molecular system. So here a sequential mechanism is shown. Basically, light strikes the metal, which is which has an interface with a molecule or maybe a semiconductor here. And that excites a surface plasmon, which then decays to produce hot carriers. And those hot carriers are finally separated because they are injected into the adjacent material. But compared to that sequential mechanism where there's a lot of possibility of losses, here we have the possible, here in C, direct excitation of hot carriers across the interface to form a charge separated state is shown, and that is the way forward to be able to get high efficiencies in the harvesting of hot carriers. So now, what's the importance of all of this for heterogeneous catalysis? Now, heterogeneous catalysis is where you have multiple phases present, where the catalyst itself is a solid typically, and then the reaction medium could be gas or liquid. So there are multiple phases involved in heterogeneous catalysis, and there's typically adsorption that has to take place, and reaction and desorption. Also, in the overall field of catalysis, this is a very commonly used picture, because a catalyst, recall, is a substance that enhances the rate of a chemical reaction without itself participating in a chemical reaction, and it does this by helping the reactants overcome the activation energy, and so it facilitates the formation of a so-called transition state, which leads to the final state. Now, something to really keep in mind is that noble metal nanoparticles, silver, gold, copper, also some base metals, nickel, other noble metals, platinum, rhodium, are already the most widely used catalytic nanoparticles that drive a variety of heterogeneous reactions that form the bedrock of modern industrial civilization. So these would include ring opening, ring closing, hydrogenation, Fischer-Tropsch synthesis, transesterification, alkylation of alcohols. All of these reactions that are used that form the staple of heterogeneous catalysis typically already use metal nanoparticles, but there the role of the metal nanoparticles is essentially to facilitate phonon-driven catalysis. And what I mean by that is that the reactants, the vibrational modes of the reactant molecules coupled to the vibrational modes of the metal nanoparticles, and as a consequence, the thermal energy that is then supplied to the metal nanoparticles is efficiently transferred to the reactant molecules, enabling them to overcome this hump and reach the final state. But this also means that the vast majority of reactions in heterogeneous catalysis use high temperatures, typically 400 degrees, 500 degrees, and there are reactions that require much higher temperatures as well. Now, one of the exciting aspects about plasmonic catalysis is the possibility of performing these reactions at close to room temperature, and therefore resulting in massive energy efficiency and potentially massive cost savings. So that is at least the potential of plasmons in heterogeneous catalysis. And here I show graphene simply because graphene is a particularly good substrate for heterogeneous catalysis because of the tunability of reaction sites. Okay. So now I move to my group's work in photocatalysis, and some of the reactions that we have been looking at are gas phase photoreduction of carbon dioxide, photoelectrochemical cells, water splitting in neutral and alkaline electrolytes, and carbon dioxide reduction in acidic electrolyte, the photochemical degradation of dyes and other organic pollutants, and surface catalytic reactions, such as, for instance, the reduction of nitrobenzene thiol to its azobenzene, etc. So all of these reactions are important. For instance, there are like 1 to 2 million tons of various organic pollutants that are discharged into freshwater sources every year, and that does not count the pollutants that are discharged into the seas, the CO2, and that is discharged into the atmosphere. So there is a huge need for photocatalysis to perform various kinds of remediation reactions, and also, as I mentioned, the potential for photocatalysis to be used in more standard industrial heterogeneous catalysis. Okay, so now I move on to some specific examples of plasmonic catalysis. And now, if you think about how most researchers in the field approach plasmonic catalysis, they take a nanostructured material. This could be a nanostructured chalcogenide or a graphene-based platform, or a metal oxide platform such as metal oxide nanotubes or nanowires, and then they decorate it with gold or silver nanoparticles. So this is the most frequently used method. One problem with this is that the high quality factors that you see in individual gold nanoparticles or lithographically defined ensembles of gold nanoparticles, you don't get to see those. So you see the plasmon resonances here are weak. In some cases, they are barely discernible. So what we did is we found a way to embed plasmonic nanoparticles inside the structures, because that helps not only with energy conservation, but with also momentum conservation. And that immediately allows us to get much stronger resonances. Resonances that are both have a higher quality factor, but also have a high oscillator strength. So, and the way we went about doing them in one case was we used electrochemical anodization to form metal oxide nanotubes, titanium dioxide nanotubes. But we changed up the process a little bit. When we sputtered the titanium film, instead of just sputtering a plain vanilla, a micron thick titanium film, we layered it with alternating layers of titanium and gold, and then so that you see you have a striated, stratified structure where you have gold layers which are darker and the titanium layers which are lighter. And then we subjected this overall stack, this thin film stack, to electrochemical anodization. And then through the processes of self-organization due to field-assisted oxidation and field-assisted etching and chemical etching, you get these vertically oriented nanotube arrays. But because we started off with the gold films layered with the titanium films, we end up getting gold nanoparticles that are either partially or completely embedded in the walls of the nanotubes. And so when you look at TEM, you can see these bands of nanoparticles. You also see them here. Okay, and this was a paper we published on this topic in ACS Applied Materials and Interfaces, where we showed reduced ensemble plasmon line widths and an enhanced 2-photon luminescence. That was a plasmonic enhancement of the 2-photon phenomenon. But we also noticed a bunch of other interesting things. There were heteroepitaxial interfaces formed between the gold and the TiO2, which we didn't expect. And of course, what we did expect was a strong enhancement of 2-photon fluorescence and Raman scattering due to the local field enhancement, and that did occur. And because both gold and TiO2 are very photochemically stable and chemically resilient, these are reproducible and reusable. So if you use them to drive a chemical reaction, for instance, all you need to do is perform an oxygen plasma treatment, and then you're ready to use these again. So that's a huge advantage. Okay, and then here are the optical properties of these gold nanoparticle embedded titanium dioxide nanotube arrays. So we initially started with somewhat broad resonances with a high oscillator strength, and then we were able to retain the oscillator strength. So the amplitude of the resonances was still strong, but we were able to narrow the full width at half maximum to get much sharper resonances, to get high quality factors. And the quality factor of the resonance is important because it's directly proportional to the local field enhancement of a plasmon resonance. And so these are some FDTD solutions, simulations showing that the cross section of the gold nanoparticles at resonance is much higher than at off resonance. We use these gold nanoparticle embedded titanium dioxide nanotube arrays for photoelectrochemical water splitting, and we saw improvements. We saw that even now, remember, titanium dioxide, even though it's very photochemically stable and an excellent catalyst, its big problem is that its band gap is too wide. It's a wide band gap semiconductor. The anatase phase has a band gap of 3.2 EV, and the rutile phase of TiO2 has a band gap of 3 EV. So which means TiO2 is not useful for harvesting visible photons. And remember, only 5% of solar energy resides at ultraviolet wavelength. So you're not using the remaining 95% of solar photons. But once we had the gold nanoparticle embedded TiO2 nanotube arrays, we were able to produce an appreciable photo response even at for blue photons, orange photons, and green photons. And this occurred because of plasmonic harvesting, because of plasmonic catalysis through the harvesting of hot electrons. The quantum yield is very interesting because now at ultraviolet wavelengths, we saw very high quantum yields, almost close to 100% at ultraviolet and blue. For blue and violet photons. That's not a surprise. That's purely due to the titanium dioxide. However, we saw appreciable quantum yields. So if you look at close to the plasmon resonance, so 490 to 495 nanometer, which is orange to green, for instance. Now we are seeing for low intensities, we approach quantum yields of 40% which matches the transient absorption papers that I alluded to earlier. We approach 40%, but the thing is, as we increase the intensity of illumination, the quantum yield goes down. So there are still issues with harvesting the hot carriers efficiently at high illumination. Now, one thing that I maybe didn't explain sufficiently is that a Schottky junction is nearly essential for harvesting hot carriers. So so here we see with gold, ruthenium, zinc, palladium, all of them, except for zinc palladium, which forms an accumulation type interface, the remaining, the ruthenium, gold, noble metals, they form Schottky junctions. And when you have Schottky junctions, it facilitates the injection of hot carriers from the metals into TiO2. And one more thing that is important is adsorption, because this is essentially heterogeneous photocatalysis. So we do care about how the CO2, in this case, I'm moving to CO2 photoreduction from water splitting. And unlike water splitting, which occurs in liquid, it's a photoelectrochemical reaction. This is a purely gas phase reaction. And the CO2 adsorption depends on the surface. So the CO2 adsorbs a bit differently in the gold TiO2, the ruthenium TiO2, and the zinc palladium, but all of them are successful in reducing carbon dioxide to methane, essentially. CuPt was the one that gave us the best performance, which isn't shown here, but that also found a Schottky junction. Okay. Now, one thing we did from a fabrication point of view to improve the yield of CO2 photoreduction was to form photonic crystals. we were able to modulate the diameter of the nanotubes in the depth direction. So you can see we were able to produce these kinds of notches. And what these notches do is they modulate the refractive index as a function of depth. So here I'm showing you a picture where you can see that the diameter of the nanotubes varies, and hence as a result you have a periodic variation in the refractive index, which acts like a one-dimensional Bragg mirror or one-dimensional photonic crystal with its characteristic iridescence, which is the angle-dependent color. Okay. Now, and the reason for this, the motivation for making photonic crystals from these nanotubes is to create an optical cavity and hybridize the plasmon resonance with the photonic stop band. And this is all done non-lithographically using a bottom-up process. So this is showing how 3 DC power supplies with the pulse generator. This was all home built. Can be used to create a pulse train, a sequence of pulses to perform pulsed anodization, and that is what results in this photonic crystal, one-dimensional photonic crystal. We have a lot of control. We have different types of photonic crystals: A type, AB type, ABC type, and now research in this area is moving from monoperiodic to biperiodic and even aperiodic photonic crystals. And we are able to get fairly good quality factors of the stop bands, fairly narrow full width at half maxima in these bottom-up solution-grown photonic crystals. Okay, now this is this is showing how they performed at prime time. So this is the photonic crystal cross-sectional view of the titanium dioxide nanotube photonic crystals. This is a schematic diagram of our photoreactor. We have CO2, we have droplets of water. The CO2 is in the gas phase. The water is converted into the gas phase, becomes water vapor. And then sunlight is incident through a quartz window, and the products of the reaction are sampled and are detected by a gas chromatograph or a mass spectrometer. And so we use the gold standard isotope labeled mass spectrometry, and in most of the junctions we studied. So either if you use titanium dioxide alone without any heterojunction, you get methane. But even if you get methane, but you only end up using ultraviolet photons. If you make junctions of the titanium dioxide with gold nanoparticles, ruthenium nanoparticles, copper platinum nanoparticles, you still get methane, but now what happens is that you get a much higher yield of methane because you're not only using ultraviolet photons, but you're also using visible photons from about the blue photons and some of the green photons as well. Okay, and there are two common pathways by which titanium dioxide reduces carbon dioxide to solar fuels, to value-added products. One is the carbene pathway, which proceeds in the following manner using the reaction intermediates listed here. So you have this methylene radical here, eventually forming methane. And this is the dominant pathway on TiO2 for CO2 reduction. There's also the formaldehyde pathway that is seen more in liquid environments, and it's seen for other metal oxides and for other semiconductors. So you have the carbene and formaldehyde pathways. Just keep that in mind. So in the carbene pathway, the only reaction intermediate that is typically observed is carbon monoxide, whereas in the formaldehyde pathway you see formaldehyde and sometimes formic acid and methanol as well as reaction intermediates. Okay, now when we take the photonic crystal that I pointed to, the one-dimensional photonic crystal, and furthermore when you arrange its stop band of such that it matches or overlaps with the plasmon resonances of the gold nanoparticles, now you have like a hybridization of the cavity resonance, the optical cavity with that of the plasmon resonance, and that results in new behavior. And the new behavior we had was a kind of a light dependent mechanism. So an optical pathway dependent mechanism. So what happened is when we use purely sunlight, simulated sunlight, AM 1.5G terrestrial illumination, indoors through a solar simulator, we get a small amount of carbon monoxide, which is a reaction intermediate, and we mostly get methane. But on the other hand, when we have a sequential illumination of first a white lamp and then sunlight, we observe an entirely different set of products. We see a much larger amount of carbon monoxide and a slightly larger amount of formaldehyde with almost no methane obtained. So this is remarkable if I can dwell on it a little bit. It's the same catalyst system which consists of titanium dioxide periodically modulated nanotubes, a photonic crystal decorated with gold nanoparticles. So in this exact same photocatalyst system, if you illuminate it with sunlight in the presence of carbon dioxide and moisture, you get methane. But on the other hand, if you illuminate it in a sequence with a white lamp and then illuminate it with sunlight, you get formaldehyde and carbon monoxide, and you get no methane. This is truly remarkable. And then when we went deeper, we found that was essentially because of the composition. The white lamp had very little ultraviolet and was richer in blue and green photons. And so what we then decided is to pry out the true behavior, we used monochromatic illumination with just 365 nanometer and 532 nanometer, and we saw the same results. When you use purely ultraviolet light, you get only methane. And when you use purely green light or even blue light, you get formaldehyde and carbon dioxide and carbon monoxide. So what this showed is that the wavelength of the light used could be used to control the reaction pathway, which is really new. So ultraviolet light leads to the carbene pathway of CO2 reduction to generate methane, and green light results in the formaldehyde pathway to produce formaldehyde and carbon monoxide. All of this was verified using isotope level mass spectrometry. The UV vis spectra were very interesting because they confirmed much higher density of injected electrons in titanium dioxide, because free electrons have this distinct near infrared signature, but that was scan dependent, and that also tells us that that there is a Z scheme operating. I won't go into too much details about the Z scheme, but I will point you to our article where we discuss the underlying phenomena in great detail. This was published in 2020, so this is very recent work from our group, published in Applied Catalysis B, which has become one of the preeminent venues to disseminate research in catalysis and photocatalysis. One more very interesting achievement that I would like to share with you is that in the same periodically modulated, in the same titanium dioxide nanotube architecture, but without the photonic crystal modulation, but when we now decorated it or infiltrated it with bimetallic silver copper nanoparticles, we saw something even more interesting. We saw the preferential production of ethane. So what I'm showing you here is when we have silver copper nanoparticle decorated titanium dioxide nanotube arrays, we see a bit more ethane production compared to methane, though methane is still produced. Whereas if you use just copper nanotubes or just silver decorated nanotubes, you see much less ethane. Now, something to keep in mind is that as you make the carbon atoms longer, carbon chain longer, the value of the product increases. So ethane is more valuable than methane because it's a precursor for a lot more industrially important products such as plastics and small molecules. But some propane and butane are even more valuable than ethane, and octane is very similar to gasoline. So our ability to make a C2 plus product, that is a hydrocarbon product with two or more carbon atoms, using light, using photocatalysis and a very cheap photocatalysis catalyst, because here silver, copper, the amount is that is used in this catalyst is actually quite small, is fairly remarkable. Last topic that I want to talk about is, which I'll go through very quickly, is graphenic semiconductor plasmon hybrids. Something that's another area that we've been working on and publishing a bunch of papers in. Graphene is very interesting because you have a different types of sites, and once you dope graphene with nitrogen, you can open up a small band gap. And also the different types of nitrogen sites in graphene. You can have a pyrrolic nitrogen, a pyrazolic nitrogen, a graphitic nitrogen, and a pyridinic nitrogen. So we were working with nitrogen doped graphene that we got from our collaborator at East China Normal University, ECNU in Shanghai. So the nitrogen doped graphene was of very high quality. It had the characteristic D and G brands of graphene. It was grown by large area chemical vapor deposition. And then those sheets were delaminated by dissolving the substrate, and that's how the nitrogen doped graphene was formed. Then we decorated it with silver and used it as a photocatalyst for surface catalytic reactions. And what happens is, when you have the silver nanoparticles, there's the possibility of exciton plasmon interactions, because the nitrogen doped graphene does have an exciton. It's a low band gap semiconductor. It has a weakly bound exciton, and that can interact with the silver plasmon. And chemical interface damping is facilitated because of the strong interaction of the exciton with the plasmon. So we used a variety of methods here, ultraviolet photoelectron spectroscopy and a Kelvin probe force microscopy, which showed a distinct photoresponse upon photoexcitation in these hybrids, the silver nanoparticles decorating the nitrogen doped graphene. And sure enough, these were excellent photocatalysts for the reduction of nitrobenzene thiol to dimercaptoazobenzene, DMAP. This is a 4-electron photoreduction process that is shown here. Light with four electrons changes the nitrobenzene thiol to dimercaptoazobenzene. And what we could see here is that the nitrogen doped graphene coupled with the silver nanoparticles was able to complete the reaction at a laser power of merely 1 milliwatt, whereas for the other ones, for just the nitrogen doped graphene alone or for the silver alone, the reactant peaks were still visible, which means that the reaction had not proceeded to completion. But when you use nitrogen doped graphene coupled with silver nanoparticles, there was a dramatic improvement in photocatalytic performance, and even at 1 milliwatt laser power, this reduction process proceeded to completion. Again, showing the power of plasmonics and hot electron harvesting for photocatalysis. So in conclusion, titanium dioxide nanotube arrays with embedded gold nanoparticles showed high quantum yields for visible light driven water splitting, suggesting efficient hot electron injection from gold into TiO2. Titanium dioxide nanotube photonic crystals decorated with gold nanoparticles showed wavelength tunable product selectivity. Nitrogen doped graphene coupled with silver nanoparticles is an exceptional photocatalyst for single electron or multiple electron surface reactions. C3N5 is a brand new graphenic semiconductor which we synthesized and disseminated in a JAX paper recently that has also shown promise in plexitonic photocatalysis. And by plexiton, we mean this coupled plasmon exciton. Graphenic semiconductors provide an excellent playground to explore plexitonic effects due to the exciton-plasmon coupling and chemical interface damping. And plasmon enhanced semiconductor photocatalysis the area as a whole offers the potential to perform a variety of industrial reactions under milder and less energy intensive conditions. So So with that, I want to acknowledge my group members here who actually did the research, and my funding sponsors. Thank you.